Hello and welcome to this video where we'll discuss how to size up gates to minimize path delay. So let's suppose you're driving a large capacitive load and you've designed the logic and now you need to figure out how to size this logic for minimum delay. So the first question you might want to ask was, how many stages should I use when I want to design this logic? How large should each stage be? And given all that, what is the fastest I can operate the circuit at, right? So these are good numbers to have in mind when we're doing quick back of the envelope kind of calculations. So let's figure out a technique that can be used to design a data path given a few constraints. But before that, let's quickly revisit logical effort and let's find the logical efforts of a couple of common gates. So again, I'm going to be discussing logical efforts in a technology where the smallest inverter is sized with a PMOS of 2 and an NMOS of 1. So remember, the logical efforts of various gates are comparing the delay in a complex gate with respect to this inverter. And so if this inverter changes, for example, suppose you're designing it for a technology where the NMOS PMOS ratios are 1 to 1, in that case your logical efforts for the various gates are also going to change because the basic inverter in a technology is different. So let's assume we have a technology where the inverter is sized to 1. So now if I look at a 2-input NAND gate, we looked at this in the last video, I will size it up such that the worst case pull-up resistance is the same as the worst case pull-down resistance is the same as that of the inverter. And so therefore my NMOS is a size 2, my PMOS is a size 2. And so if I now talk about the logical effort of this NAND 2 gate, it's essentially, or rather the RC product of the complex gate compared to the RC product of the inverter. In this case, at every input, my net input capacitance is 2 plus 2, so that's going to be 4. So it's 4C times R divided by 3C times R, and hence the logical effort of this gate is 4 by 3. Now I could design a NAND gate in this technology which looks something like this. That is, instead of all the NMOS size 2, I will have a NAND gate with all the transistors sized 1. Now obviously this gate is not optimal because here if you look at the delay in this gate, you're going to see that because of the fact that you've sized the NMOS transistors as 1 and 1 and the PMOS transistors also 1, this is going to have a worst case pull-up resistance which is twice that of the inverter, right? So we would expect the delays in this gate to be longer. But nevertheless, let's look at the logical effort. If you look at the logical effort of this gate, again, if you look at the total input capacitance at every node, it's going to be 1 plus 1, which is 2. But this is now going to be multiplied by the pull down or pull up resistance, which is not R in this case, but 2R. So it is twice that of the inverter. And you normalize it to that of the inverter. So again, you get a logical effort which is the same as 4 by 3. So an important part to remember is that the logical effort of the gate is purely related to the way the NMOS and PMOS transistors are sized. It has got nothing to do with the actual size of the transistors, right? So it's the ratio between the N and P that modulate the logical effort of a gate. Now let's look at a 2-input NOR gate. If you look at a 2-input NOR gate, again here we size it up for the same worst case pull-up or pull-down resistance as that of the inverter. And so because we have a PMOS stack, we size it up to 4, 4, the NMOS is 1, 1, leading to an input capacitance at every node to be 4 plus 1 or 5. So it's going to be 5C into R divided by 3C into R, giving you an logical effort of 5 by 3 at every node. Now let's consider another gate, and this is the A into B plus C complement, right? So here I have a pull down network which consists of A connected in series with a parallel combination of B and C. So either AB is going to provide a pull down or AC is going to provide a pull down. And so if I'm now going to size up the pull down stack, in the worst case, the pull down stack consists of 2 NMOSs connected in series, and so I will size them up as 2 and 2, that is twice the width of the NMOS in the inverter. Now similarly, if I look at the PMOS in this case, Now the PMOS path is different, right? So in the worst case, I can either have a pull up through A or I can have a pull up through the BC combination. So if I have a pull up through A, then I size the PMOS, which has the input A, to the same as that of an inverter, because this consists of only a single pull up transistor. However, if I'm going to do a pull up through the BC network, then the BC network has to be sized larger so that the effective resistance of the series stack of PMOS stays the same as that of the inverter. So what you see here is that the PMOS transistors are sized up differently for the different input nodes. And so therefore, if I find the logical effort for input A, the input capacitance is 2 plus 2 times the pull down resistance or the pull up resistance, which is going to be R. Compare that to the inverter. So the logical effort for the input A is going to be 4 by 3. Whereas if you look at the logical effort for input say B or C, both B and C have an input capacitance of 4 in the PMOS, 2 in the NMOS, giving it an input capacitance of 6C. So this 6RC normalized to 3RC gives you a logical effort of 2. So in gates, you'll sometimes see that the logical effort can vary across inputs, right? And so depending on which input of yours is in the path you're minimizing for, you need to make sure that you're using that appropriate logical effort in your calculations. Now let's look at a 3-input NOR. A 3-input NOR is going to be sized up as it has a PMOS stack of 3 transistors. You size it up so that each PMOS is thrice that of the inverter PMOS. So this is sized to 6, 6 and 6. Worst case NMOS pull down has a single transistor. And so here every node again has 7C. And so your logical effort is going to be 7/3, right? So please remember that logical effort is related both to the input capacitance and to the pull up and pull down resistance in the gate. And this is because we are trying to normalize all gates to this basic unit of digital design, which is the 2-1 inverter. So now let's put together the problem statement. So basically we now have to say design a cascade of gates driving a load. So that is my problem. And I want to figure out how am I supposed to size up these gates so that this delay is not too long. Now let's think about any gate in particular. So if I want to make a gate faster, the simplest way to do it would be to size up its transistors larger. So if I make the NMOS and the PMOS larger than what is required, then basically I improve the drive current of the gate, leading to a smaller delay. However, for example, suppose I size up gate 2. I will make gate 2 faster, but by sizing up gate 2, I will increase the load on gate 1, and that might, so sizing up gate 2 has an impact on the delay on gate 1, right? So whenever you have a cascade of gates, you can't really size the gates in an isolated fashion. You need to figure out how the change in the size of a particular gate affects the preceding and the succeeding stage. So let's assume that we want to drive a capacitance whose normalized value is say some output CO, right? And typically if you look at any path you'd like to design, just like how we discussed about gates, normally any path will also have an input capacitance requirement. That is because this input capacitance for this path is going to be an output for a preceding path. So normally you bound the path with an input capacitance and an output capacitance. Because of the fact that when we deal with delays, etc., we're dealing in normalized quantities, we typically consider the normalized quantities for these capacitances, which means we will normalize it to the input capacitance of the inverter. So let's follow a convention. So if I put a number X at the input of a gate, that means that the gate capacitance at that node is X times the gate capacitance of the smallest inverter, right? So it is telling you how is this input cap with respect to the smallest inverter that we have in the technology. So let's put those together. Basically, we want to find X, Y, and Z. So we're given CO, we're given CI. We need to determine the values of X, Y, and Z so that the delay through this path is as low as possible. So let's first talk about the electrical efforts of every gate. So if you look at the electrical effort of gate 1, the electrical effort of any gate is defined by the work that the gate has to do, and it is related to the ratio of the output capacitance to the input capacitance. Again, a refresher, the output capacitance is the capacitive load that we are trying to drive. The input capacitance is a measure of the size of the transistor that is driving that load. So a ratio tells you the net effort this gate has to make on the load at the gate, right? So if I label the electrical efforts as H1, H2, H3 and H4, the electrical efforts are going to be just the output of the gate divided by the input of the gate. So for example, if I look at gate 3, the node at the output of gate 3 sees an input capacitance of Z from the gate 4, and the input capacitance of gate 3 is Y, and hence the electrical effort associated with gate 3 is going to be Z upon Y. Now let's assume that each of these gates have a certain logical effort. So each of these gates is going to have logical efforts numbered G1 to G4. And let's also assume that each of them have certain parasitic delays, again numbered from P1 to P4. So now if I look at the electrical effort of the entire path, right, that is how much does this path have to work towards driving this output load, then the total electrical effort in the path, extending the concept from a gate. So the electrical effort of the path is given by the ratio of the output capacitance of the path and the input capacitance of the path, and its product of the individual electrical efforts. Similarly, we'll call capital G the product of all the logical efforts in a given data path. And so the path effort is going to be given by the product of G and H for every gate, and the path effort for the entire path is just the product of the individual path efforts, which is nothing but the product of Gi Hi, or in this specific case we have the path effort, which is going to be a product of G and H. So I'd like to note that this H, the electrical effort of the path, is independent of sizing. Similarly, we just discussed at the beginning of this talk that the logical effort of the gate is also independent of sizing, which means the path effort is essentially independent of sizing. The path effort depends only on the electrical effort of the path. Now, if you look at the delay for any stage I, for any stage I, the delay or the normalized delay is given by Gi Hi plus Pi. So Pi is the parasitic delay, Gi is the logical effort, and Hi is the electrical effort of that stage. And so the total delay in the path, which is again denoted by capital D, is given by the sum of the individual delays of the gates, and hence it's going to be given by two parts. One is the sum of all the parasitic delays, which I'll club into a letter P, and then the sum of all the effort delays of the gates, which I'm going to sum into df. And our goal is to minimize df given that the path effort is a constant, right? Or in other words, we want to minimize a sum given that its product is a constant. So how do you go about doing this? So when we want to minimize a sum given its product is constant, it's a very well-known optimization problem. And the sum is minimized when the delays, effort delays of every stage are equal to each other. And therefore I can write the effort delay of the optimal effort delay of a stage to be given by the 1 by nth root of f, where n is the number of stages available in the path. And so therefore the minimum delay in the path is given by n times f to the power 1 by n plus the parasitic delay. So this is the minimum delay that you would get, and this minimum delay is again independent of the sizes of the gates. It's only dependent on the path effort delay. Once we have the delay of the individual gates, we can now go ahead and size the various gates for the specific delay, right? So this effort delay is the optimal delay that every gate must have. And let's illustrate this problem with an example. So let's assume that we have a path which has an input capacitance of 12 and needs to drive a load of 1382.4. Now again, we are looking at technology in which the smallest inverter is size 21 and has an input capacitance of 3, right? Which means that if I look at this input capacitance of 12, this inverter is essentially sized up to 4 times the smallest inverter. We have 4 stages in this path. Basically, this inverter, the NAND gate, the NOR gate, and the second inverter. Let's assign input capacitances to every node here. So this NAND gate has an input of X, NOR gate has an input of Y, and the inverter has an input of Z. Number of stages are 4, and the total electrical effort of this path is independent of sizing, and it's given by the ratio of the output capacitance to the input capacitance, which is calculated as 115.2. Now let's look at the logical efforts and the parasitic delay. So the logical effort for each of these gates stage wise is given here. The inverters have a logical effort of 1. This is a 2-1 technology, so the NAND is a faster gate, has a logical effort of 4/3, and the NOR has a logical effort of 5/3. So the logical effort in the path, which is given by the product of all these logical efforts, is 20/9. Similarly, the parasitic delays, the NAND 2 and the NOR 2 are complex gates, and their delay is twice that of the inverter. So the total parasitic delay in this path is 6. In reality, this would be 6 tau inverter, but since we have normalized at the delays, so this is going to be 6. Now therefore, the path effort is given by the product of G and H, which is given by 20/9 into 115.2, or it's given by 256. So 256 is the path effort. And therefore now we have 4 stages in this path. So the optimal effort delay per stage is given by the path effort to the power of 1/4 or 4. So 4 is the optimal effort delay per stage in this particular data path. So now that we have the optimal effort delay, we can go back and start calculating the sizes of the various gates. So let's start with the last stage, right? So the last stage, if you look at the last stage, this Z inverter. So now the effort delay of this last stage is given by G3 into H3. G3 is given essentially by 1, because this is the logical effort of this inverter, and the electrical effort of this inverter is 1382.4 divided by Z, and this effort delay of this stage should be 4, which gives us Z to be 345.6. Now remember that once we know Z, Z is the input capacitance at this node, and we know that in an inverter the input goes to a PMOS and an NMOS. A PMOS that is twice the size of the NMOS. So once we know the ratios of the PMOS and the NMOS, which is 2 and 1, I can calculate the width of the NMOS to be 1/3 of the Z, which is 115.2, and the width of the PMOS to be twice that of the NMOS, which is 230. So this is the largest inverter in the stage, and it's given by a PMOS width of 230 and an NMOS width of 115. Now that we know the input capacitance of at Z, we know the output capacitance of Y. So now we use a similar argument to calculate the size of Y. So again here, if you look at the effort delay of this stage, it is G2 times H2. Again, the logical effort of the NOR gate is 5/3. The electrical effort of this gate is Z upon Y, which is 345.6 upon Y. And this effort delay again should be 4, which gives us the value of Y to be 144. Now this is a NOR 2 gate, and when we design a NOR 2 gate in a 2-1 inverter, we essentially design it such that the PMOS is of size 4 and the NMOS is of size 1. So therefore again Y is going to be the input capacitance of both the PMOS and NMOS combined. So it's going to be 5 times the capacitance of the NMOS. So therefore the NMOS width is given by 144/5, which is 28, and the PMOS width is given by 4 times the NMOS width, which is 115.2. Now that we know Y, we can go back and now calculate X by again looking at the effort delay of the NAND 2 gate, which is given by G1 into H1. So that's 4 by 3 into 144 by X. It's equal to 4, gives us X as 48. This is a NAND 2 gate, and in the NAND 2 gate, both the NMOS and PMOS are sized equal of 2 and 2. Therefore, the NMOS is sized at 24 and the PMOS is sized at 24. Right? So by knowing the input and the output capacitance and the various gates available in the path, one can calculate the delay of the path. So the minimum delay in this path is therefore going to be given by 4 stages times 4. That is going to be the minimum effort delay, which is 16. And the parasitic delay in this path is essentially 1 plus 2 plus 2 plus 1, which is 6. And so the delay is going to be 16 plus 6, or 22 tau inverter, or 22 times the inverter delay. Let's consider a path that we want to optimize here. And the path here basically consists of 2 stages. A stage of an inverter which then feeds into 2 other inverters of similar size. Right? Now in this case, because the path is only made up of inverters, we can say that the electrical effort and the effort delay are the same because the logical effort of inverters is 1. So if I look at the electrical effort of stage 1, it is nothing but 2 times X divided by A, since the output capacitance of stage 1 is contributed by the input capacitance of this inverter and this inverter. The electrical effort of stage 2, however, in this path is only given by Y by X. Now if I consider a path which includes this inverter and the following inverter here, the total electrical effort across the path is given by Y by A, and that is not equal to the electrical effort of the first stage times the second stage. And that is because the first stage is driving a larger capacitance than what is in the path, right? Because the first stage is driving 2 inverters here, it's driving a larger capacitance than whatever is included in the path. And so therefore in this case, we talk about a branching effort. So at any time the path has a branch, we account it by using a branching effort, which is defined as the total capacitance that is present at the branch divided by the capacitance that is in the path that you're optimizing for. If you have multiple branches in your path, then every branch will have a branch effort, and the branch effort of the entire path would be given by the product of the individual branch efforts. In that case, the path effort will no longer just be G times H. It is given by G times B times H, where B is the additional effort required due to the branching present in the path. Let's change the problem a little bit. Now let's assume that we have designed a logic block with some N1 stages that is driving a large capacitive load. Now the question is this good enough, or can we optimize the delay further by adding more stages to this path? Right? So what we are trying to understand is, suppose I add a few inverters to this path, then essentially I'm now adding more stages. Is this design give me a better optimal point for delay as opposed to one without the inverters? Any number of inverters can be added without any loss to the logic functionality. Right? So let's assume we have added n minus n1 inverters to the path, which means the total number of stages in this path is n. Now let's assume that the path effort of this particular path is f. So if we're now going to talk about the optimized delay of this n stage chain, it is given by what we just discussed previously in the video. D is given by the optimized effort delay, which is n times f to the power 1 by n, plus the parasitic delay that might be associated with any complex logic gates present in this block, plus the parasitic delay associated with these additional n minus n1 inverters that I have added to the path. Right? So even though this is optimized, there is an increase in the delay because of the parasitic delays associated with every stage. So now what we need to do is we need to see if this function that is given here, if this function has a minimum at any given value of n. So is there a capital N here which minimizes this function? So let's take a look at this function and differentiate with respect to n and set the first differential to 0. Now if you set this particular term rho to be the 1 by nth, the nth root of f, what we essentially break down is we need to solve this transcendental equation where rho into 1 minus ln rho plus p inverter is 0. Now graphically if you look at this, it turns out that the solution for rho versus p inverter, rho to be roughly equal to around 3.5 or 3.6 for a p inverter of 1. And then if you assume that the p inverter is longer, then the rho changes slightly. If you now look at this function, so this point, so for example for p inverter equal to 1, this 3.6 something is the minimum value for rho. And now if you look at the value of this function, right, around this optimal value of rho, what we see is if I plot the function around the optimized function versus the ratio of n to the optimized number of n, we see that this is the way the function looks like. So you see as rho varies from 3 to 4, around 3.6, which is where the optimal lies, you have a pretty slow varying function around a very large change in the number of stages. The curve around the optimum is pretty flat and the delay is within 15% for a large change in n. What we do in this case is we choose a stage effort of 4 just because 4 is a nice integer to keep in mind and it's a convenient choice. What we see is that between rho equal to 4 and 3.59, there isn't a much of a difference in the value of the minimum function. So hence the number of stages that are required for a minimum delay is just given by log to the base 4 of the electrical effort delay. That is, we design the path in such a way that every stage has an effort delay of 4, then we would be achieving the fastest circuit, or in other words the delay being minimum at that point. So this stage effort of 4, that is an inverter with a fan out of 4, sometimes becomes a representative of the delay in logic in a given technology. So sometimes we use FO4 inverter delay as a metric when you're comparing across various technologies. So before we conclude, I'd like to highlight some of the limitations of the linear delay model that we've looked at in the last few videos. The first thing is this linear delay model, that is the Elmore delay, the RC delay, and eventually what we've done here for optimizing for path delay, it does not capture the effect of the input slope. So the input slope actually does change the propagation delay of the gate, and so it's many a times when you look at complex gates, this effect of input slope becomes important to actually account for the delay in the gate. The model also does not capture any impact of variation at the input arrival times. And so therefore what happens is that it might overpredict or underpredict in certain cases, which may not be true. So when we do these predictions, you have to be careful, especially when we're looking at stacked transistors or when we're looking at transistors connected in parallel. The third and very important thing is that it does not capture velocity saturation, right? And so when we assume that we have connected n transistors of gate length L, it doesn't mean that this is equivalent to a transistor of gate NL, because when transistors are velocity saturated, the effect of L on the drive current is not as pronounced as it is in the square law model. And finally, the model does not capture voltage dependence. So VDD is a very important parameter. It's an important knob that we generally use when we want to improve the performance of a block. And that is something that cannot be captured by this linear delay model. So to conclude, logical effort provides a very quick and dirty way to compare designs or circuit topologies, and it helps us design a path for a minimum delay most importantly using hand calculations. So it gives you a feel as to how should you design the path for an optimal delay. Now the path delay that we have calculated is insensitive to modest deviations, and therefore this it makes the method even more powerful because it gives you a rough ballpark area of what the path should look like. And therefore, it also tells you that when you want to choose transistor sizes, we don't need to be exactly driven by the hand calculation, but choose numbers close enough to those that are given by your optimal design. And this can be rounded off based on what is allowed in the design rules. And the general rule of thumb is that to use a stage delay of 4 to capture minimum delay in a given path.